Hello everyone, and welcome to today's session. We'll be exploring the Spearman rank order correlation, often simply referred to as Spearman's row. What is Spearman's rank order correlation? This is a non-parametric measure, which means it does not rely on the assumption that the data must follow a normal distribution. Instead, it is more flexible and can handle data that do not meet the strict requirements of parametric tests. Spearman's row is particularly useful when working with ordinal data, that is, data based on ranks or ordered categories, such as customer satisfaction ratings, class standing, or competition results. It can also be applied to continuous data that do not follow a normal distribution. This makes it a powerful tool when the traditional Pearson correlation is not appropriate. Now let's look at the conceptual foundation of Spearman's row. Unlike Pearson's correlation, which uses the actual numerical values, Spearman's row is based on ranking the data. This means we don't focus on the raw scores themselves, but rather on their positions when ordered. Another important point is that Spearman's row evaluates monotonic relationships. This means it looks at whether two variables tend to move in the same direction, either increasing together or decreasing together, even if the relationship is not perfectly linear. For example, the more time a student spends studying, the higher their test scores are likely to be. The pattern may not form a straight line, but as long as the trend moves consistently in one direction, Spearman's row can capture that relationship. Before using Spearman's row, there are some assumptions we need to consider. The most important one is that the data should be at least ordinal. Ordinal data means the values can be ranked or ordered, but the exact differences between them are not necessarily equal. For example, customer satisfaction levels such as satisfied, neutral, and dissatisfied can be ranked, but the gap between them is not a precise measurement. As long as the data can be ranked meaningfully, whether it is ordinal or non-normally distributed continuous data, Spearman's row can be applied. Another key assumption of Spearman's row is that the two variables should have a monotonic relationship. This means that as one variable increases, the other consistently increases or consistently decreases. The relationship does not have to be perfectly straight, but the trend must move in only one direction. For example, if study time increases, test scores may also increase. That's a positive monotonic relationship. On the other hand, as stress levels increase, productivity may decrease. That's a negative monotonic relationship. If the relationship between variables changes direction back and forth, then Spearman's row may not be the best choice. Another important feature of Spearman's row is that it can handle tied ranks. In real data, it's common to have the same value appearing more than once. For example, if two students both scored 15, they would tie for the same position. Instead of assigning different ranks randomly, Spearman's row method assigns them the average of the ranks they occupy. In the table shown, you can see how tied values are treated, like two scores of 23 or several scores of 15. Each tied score is given the mean of the ranks it covers. This ensures fairness and accuracy when calculating the correlation. Let's look at the formula for Spearman's row. As shown, a row is equal to 1 minus the quantity, 6 times the summation of the square of d divided by n, times n squared minus 1, where rho represents the Spearman correlation coefficient. D is the difference between the ranks of paired values for each observation. This is the total number of paired observations, and summation of d squared represents the sum of the squared differences in ranks. Building on our understanding of Spearman's row, let's look at a practical example of its step-by-step computation, specifically when there are no tied ranks. As shown in the slide, our data set explores the relationship between students' ranks in mathematics and physics. This slide provides a detailed breakdown of the computational steps. For Spearman's rank order correlation, using our example data set of student grades in mathematics and physics, here we see a table illustrating the process for each student from A to H. Each row represents a different student. Math grade, X, and physics grade, Y. These are the raw scores for each student in the respective subjects, rank X and rank Y. This is where we assign ranks based on the raw grades. As stated, we assign 1 to the smallest value, 2 to the next, and so on. Then, we compute the difference between the math rank and the physics rank for each student. For instance, for student A, the math rank is 7 and the physics rank is 8. So the difference D is 7 minus 8, which is equal to -1. Here, each difference D is squared. For student A, -1 squared is equal to 1. Squaring these differences ensures that negative and positive differences contribute equally to the total sum and removes the effect of direction. Finally, the sum of the squared differences, 3 twice 8. Now that we've calculated the sum of the squared differences from the previous steps, this slide demonstrates the final crucial step, applying the formula to derive the Spearman's rho. Recall the formula. Rho is equal to 1 minus the quantity 6 times the summation of the square of C divided by n times n squared minus 1. Let's plug in the values we've obtained. From our previous calculations, the summation of d squared is 8, and the number of paired observations n is 8. Substituting these into the formula, here, we multiply 6 by the sum of the squared differences, 8, giving us 48 in the numerator. In the denominator we have n, which is 8, multiplied by n squared minus 1. The square of 8 is 64, and 64 minus 1 is 63. Next, we multiply 8 by 63, which gives us 504. Now, we perform the division. 48 divided by 504 equals approximately 0.095. Finally, we subtract 0.095 from 1. This results to the Spearman's rho value of 0.90. With our calculated Spearman's rho value of 0.90, the next crucial step is to interpret this result. This slide guides us on how to understand both the direction and the strength of the correlation. First, let's consider the direction of relationship. The direction of relationship could either be a positive monotonic relationship, a negative monotonic relationship, or zero relationship. Positive monotonic relationship is the movement of variables in the same direction. A negative monotonic relationship is moving in opposite directions, while zero relationship means no meaningful connection between the variables. Next, let's assess the strength of relationship using the provided table. Positive or negative 1 suggests a perfect correlation. Positive or negative 1 to 0.3 suggest a weak correlation. Positive or negative 0.4 to 0.6 indicate a moderate correlation. Positive or negative 0.7 to 0.9 suggest a strong correlation, and 0 indicates weak or no correlation. Beyond simply calculating the correlation coefficient, it's essential to determine if this observed relationship is statistically significant, or if it might have occurred purely by chance. This slide introduces the concept of testing the significance of the correlation, primarily through the p-value. The p-value is a statistical measure that helps us determine the probability that an observed correlation is the result of random chance. The process of testing significance generally involves 4 steps. 1. State the hypotheses. The null and alternative hypothesis. Null hypothesis, HO. True population correlation, rho, is 0. On the other hand, the alternative hypothesis, HA, states that the correlation is not 0. In interpreting the p-value, the decision as to the acceptance or rejection of the null hypothesis is based on the following rules. If the p-value is equal to or less than 0.05, a commonly used significance level, denoted as alpha, then we reject the null hypothesis. This suggests that our observed correlation is statistically significant and is unlikely to be due to random chance. In essence, there's a real relationship. However, if the p-value is more than 0.05, then we accept the null hypothesis. This means that our observed correlation is likely due to chance, and there is not enough evidence to conclude a significant relationship in the population. In summary, The p-value provides a probabilistic basis for deciding whether our calculated Spearman's row represents a genuine relationship or just a random occurrence in our sample. Following our discussion on the p-value and hypothesis testing, this slide focuses on how to determine the p-value for our Spearman's row correlation. The slide illustrates that calculating a p-value often involves using statistical tools or calculators. Here we used a generic p-value calculator. Upon entering the data, the p-value calculator provides the p-value results. Degrees of freedom, df, is 6. The degrees of freedom are typically calculated as n-2 for correlation coefficients, where n is the number of observations. Since we had 8 students, df is then equal to 6. The calculated p-value is 0.0023. Finally, the slide presents the decision. Reject the null hypothesis, which states that the true population correlation, rho, is 0. This decision is made by comparing our calculated p-value, 0.023, to the standard significance level, alpha of 0.05. Since 0.023 is much smaller than 0.05, we have strong evidence to reject the null hypothesis. This means that the correlation of 0.90 we found between math and physics ranks is statistically significant and is highly unlikely to have occurred by random chance. This final slide brings together all our findings to provide a comprehensive interpretation of the Spearman's rank order coefficient of correlation between math and physics. Let's break down the conclusions. A value of 0.90 indicates a very strong positive relationship. As we learned from the interpretation guidelines, a correlation coefficient of 0.90 falls into the strong correlation category, and its positive sign confirms the direction. The slide further emphasizes this as very strong. This means that students who perform well in mathematics are highly likely to perform well in physics. This statement reinforces the practical implication of the strong positive correlation. It suggests a consistent pattern where high achievement in one subject is associated with high achievement in the other. Conversely, students who perform lower in math also tend to perform lower in physics. This suggests that if students struggle in math, then they are also likely to struggle in physics. The relationship holds true across the performance spectrum, based on the calculation of the p-value, which was exceedingly small, 0.0023, and far less than our conventional significance level of 0.05, leads us to confidently declare the correlation as statistically significant. The correlation is unlikely due to chance. This is the direct implication of a statistically significant p-value. It means we have strong evidence to believe that this observed relationship is not just a random occurrence in our sample, but reflects a genuine association within the broader student population. In the context of our analysis, the robust correlation indicates a meaningful connection between academic performance in mathematics and physics. Thanks for learning with us today. If you found this video helpful, don't forget to give it a thumbs up to show your support. We'd also love to hear from you, so feel free to share your thoughts, questions, or insights in the comments. And of course, hit that subscribe button to stay updated with more lectures in mathematics, statistics, and education. For more learning content, visit and subscribe to my YouTube channel. See you in the next lesson.